today we're going to be talking about many-body effects in quantum mechanics. Right.
Okay.
So many-body effects in quantum mechanics is quite different from classical mechanics. In classical mechanics, what do we do when we have a many-body problem? We start using statistical physics because we cannot specify each degree of freedom for every body in the system. So we start using statistical physics, and we extract using the concept of a temperature. We extract the important features of a many-body system. In the quantum mechanics, we do something similar, but you'll see that the quantum mechanical many-body problem is quite distinguished from the classical one, and that is mainly due to the problem of indistinguishability. So let me first talk about why we need to study this many-body problem. Well, so far, the only many-body problem you have seen is the problem of the electromagnetic field, in which you have a bunch of photons, and you can think about that as being a many-body problem. Well, but in general, us being electrical engineers, we study the motion of electrons in solids and so on. Even if you study the motion of a single electron, a free electron, because it has charge, it's inevitably coupled to its electromagnetic environment. So every problem involving charge must be a many-body problem, and we can only get back to those quantum mechanics that we have been doing by approximating. So every problem is inherently many-body. And this is especially true in solid-state physics, which we care about. So this is why we need to study many-body problem. And then now, let's think about when do we need, for a many-body problem, where is the bridge between the classical problem and the quantum mechanical problem? And for that, I need to invoke something called the Competition Serum. Suppose we have a collection of particles that is still in the classical regime. Then in the classical regime, I can write, loosely speaking, that each particle, the energy of one particle, is given by 2/3 of kBt. And this statement is called the equipetition theorem. It says that since each particle by itself, a point particle, has 3 degrees of freedom corresponding to its 3 coordinate axes, then by equipetition, every degree of freedom in an environment at temperature T gets an energy of 1/2 kBt. So I have this relation. Now let me relate this to quantum mechanics. Well, let me rewrite the energy of the particle as its kinetic energy. So we're considering a collection of non-interacting particles. So this goes to p squared over 2m, right? This is true classically, correct? Okay, now let me introduce quantum mechanics by saying that p squared over 2m is equal to h bar squared k squared over 2m, something like this. Or I could use the Broglie relation, saying that lambda is equal to h divided by p, right? Which is the wavelength of the particle, correct? Right, so either way, I introduce quantum mechanics by introducing h or h bar. Right, so let me use this because it's simpler. Written in this way, p is equal to h over lambda. So I plug this into here, I get that h squared over 2m lambda squared is 2/3 kBt. So in this way, I can relate the wavelength of the particle to the temperature of its environment, right? And this is the concept of a thermal wavelength. So after doing some algebra, what you get is lambda is equal to, let's see, you have m kBt me use a conventional notation. I'm going to, instead of write kBt, I'm going to take this to be tau. So basically, I'm measuring temperature in terms of kB, which is the natural unit to do. Right. So then we get that lambda is equal to the square root of 3m tau divided by h squared. I mean h squared divided by this. Okay. So what does this say? Well, as the temperature increases, the thermal wavelength of the particle decreases. This should make sense to you because as the temperature increases, the particle on average gets more thermal energy. And as the energy gets, and since we're only considering about kinetic energy, what do we know about particle? When the kinetic energy is higher, it's more localized. It's more particle-like, right? And also, this thermal wavelength is inversely proportional to its mass, square root of its mass. So let's connect this to a many-body quantity, which is the density, the particle density. So let me say that, well, roughly speaking, each particle is going to occupy a volume of lambda cubed inside of the solid or whatever their environment, right? Then this is equal to h squared, right? Right. So now, what is the density? The density is, this is the volume occupied by one particle. The density is then the V, the volume of the total thing divided by the volume of one particle, right? Which is equal to the density. And we can deduce from here that you have N is equal to V divided by H squared. Is that correct? Yeah. So let's rewrite this as V times 3m. So now we establish a relationship between the thermal wavelength of the particle and the concentration, the concentration and the temperature, right? So we call this term, and when this tau is taken to be the thermal wavelength of the particle, we call this concentration the quantum concentration. Right? So let me denote this by AQ. And the significance of the quantum concentration is, given a temperature of the environment, if the concentration of the particle reaches the quantum concentration, then because on average each particle is so close to the other that you need to start thinking about their wave behavior, because the wave particles dwell in quantum mechanics, then quantum mechanical effects start becoming dominant. All right? So this is one way to look at it. Another way to look at it is, given a collection of particles that have a certain density, let me deduce the temperature at which quantum mechanical effect becomes apparent, becomes dominant. So this is just done by inverting this relationship, which is thank you to the 2/3. Thank you. Yeah, is that correct? Okay. So that given the mass of the particle, and given its concentration, right? This is no longer the quantum concentration because now this is concentration we're varying. Given the concentration and the mass of the particle, we can use this relationship to deduce the temperature at which quantum mechanics becomes apparent. And you can see that it must be that the temperature must be lower than some limit, must be lower than this limit for the quantum mechanical effect to become apparent. So now I can plug in some numbers. Let me use V to let me take V to be 1 square cubic centimeter. Then the density, let's say in a solid, right? In a solid is about how many particles, how many atoms per cubic centimeter in a solid. Turn to the 23rd. Per cubic centimeter. Alright. So now let me plug in the value for H, and let's use mass as the proton mass. So I'm talking about a collection, a solid made of protons or hydrogen or whatever. Right. So then I can get this empirical relation saying that T measured in Kelvin, okay, is approximately equal to 20 divided by A, and 20 is dimensionless now, and this A is the relative atomic mass. Okay? So how much it weighs in atomic units. Okay? So atomic mass is so mass of the proton is taken to be 1, and A is the ratio between. So if you have helium, it will be 4. If you have carbon, it will be 12. So on, right? So let's think about for an electron, and this the unit would be the temperature is measured in Kelvin. So for an electron, what is the electron mass relative to the proton? It's about so m electron in this unit is about 1/1800, right? So now you get that for an electron, if we are below a temperature, if T is less than 20 times 1800 Kelvin, so this is an extremely large temperature, extremely high temperature, the electrons behave quantum mechanically inside of a solid, right? So now, of course, no solid will stand this kind of temperature. So for us, if we're studying electrons in a solid, and we're considering a pretty high concentration of electrons, so maybe in a metal, the electrons are always quantum mechanical, right? So this is for the electrons. Well, the other constituent of the solid is the nuclei. Now, if we think about this nuclei of silicon, for them to behave quantum mechanically, for their thermal wavelengths to smear out enough so that relative to their lattice spacing, you need to consider a quantum mechanical effect. This temperature will be extremely small, right? Because silicon is, I don't know what the relative atomic mass of silicon is, but it's going to be greater than 20, right? So this is less than 1 Kelvin. So actually, in the solid state, you do not need to consider quantum mechanical effects for the nuclei. So, so our picture of the solid state, if you try to incorporate quantum mechanics into it, is something called a semi-classical picture. And in this semi-classical picture, we treat the electrons quantum mechanically while we treat the lattice completely classically. The only bit of non-classicality for the lattice is what? When we quantize the phonons. We consider lattice vibration and we quantize the phonons. Professor, did you talk about quantization of phonons?
Just heuristically. We
Okay.
talk about the linear atomic chain and
All right.
quantize the linear atomic chain, then it's a phonon.
Okay.
It's a very simplified phonon model.
Okay. Right. So this is give you an idea of when does the quantum mechanical effect become dominant in a many-body problem. So so now you should remember this formula. So now let's start thinking about what are the quantum mechanical many-body effects. Well, the first thing we know is we have seen there's something called the zero-point energy, which if you do the quantization of the free field or the phonon field, you see that, well, even if there's no excitation, you still get this 1/2 h bar omega thing. This is one thing coming from a many-body effect in quantum mechanics. And even if you just have one oscillator, you still have this. But it becomes apparent if you have a bunch of oscillators. Now another thing is indistinguishability. And what do I mean by indistinguishability? Let's think about by what mechanism can we distinguish two particles that are apparently identical in classical mechanics? Right. So in classical mechanics, why can we distinguish identical particles? So I have a particle of mass m and volume v here, and exactly the circle, the shape is exactly spherical, and then I have one copy of it here. And I consider their collision or their scattering. I can always distinguish these two particles by, one thing I can do is I can color one particle green and color one particle red. Right? So they're always indistinguishable. What happens when we go down to the quantum mechanics? Right? So So this is classical mechanics. And maybe I can use color to distinguish it. Now, as I go down to quantum mechanics, there's certainly no way to color an electron. Right? And the reason is actually there's a reduction in the degrees of freedom. Right? So reduction in number of degrees of freedom. So previously, when I was in the classical regime, and I have two particles, two macroscopic particles that are made up of millions and billions of atoms. There are, for a rigid body, there are really only 6 degrees of freedom that I consider in terms of the dynamics of a rigid body. Right? But then you have all these leftover atoms, each constituting a degree of freedom. And you can change those degrees of freedom. You can change a portion of them by coloring it. You can think not necessarily about a complicated picture of coloring it. It's attaching a dye molecule to some of the atoms, right? Then this coloring thing, because of the sheer number of degrees of freedoms, when you color a fraction of them on the surface, you're really not changing the dynamics of these two balls when they're colliding. But now when you reduce the number of degrees of freedom and you're down into the quantum mechanical limit, you can no longer do this. So reduction of the number of degrees of freedom is one thing that leads to indistinguishability in quantum mechanics. Another thing that's perhaps more fundamental is coming from the uncertainty principle. And what does the uncertainty principle have to do with this? Well, without coloring the two spheres in classical mechanics, there's also one way for me to distinguish them. Right? I could just make a movie of the experiment, whereby they collide with each other and scatter off of each other. So in classical mechanics, maybe I have a setup like this, and the two particles are incident upon each other. Right? And then as they collide, maybe particle 1 gets deflected by some angle, and then to convert momentum, particle 2 gets deflected by some angle. So this is particle 1, this is particle 2, right? Now, in terms of the experimental outcome, I can say that one particle goes in this direction, and another particle goes in the opposite direction. And there's also another alternative to this. Well, maybe this particle is scattered like this, and then this particle is scattered like this. Right? In classical mechanics, because I can make a movie of the experiment, right, then in principle I could distinguish these two. Right? But now, if we're down to the quantum mechanical limit, can you still make a movie of some particle moving? No, right? Because that would require you to know the position and momentum of the particle at each point. Alternative principle tells you that you cannot trace the trajectory of the particle. So if they're scattering, right? In the quantum mechanical limit, you have two particles that are scattering. And what the uncertainty principle does is it places a screen at the place where they scatter, and you cannot distinguish between these two alternatives. All you see is a particle. Well, over here you're sure that one particle is incident from this side, so we have this information, and one particle is incident from this side, and we have this information. But in the scattering region, you have there's a screen placed by the uncertainty principle, whereby you cannot really observe the system without disturbing the scattering mechanism. Right? So all you see is that two particles come out, and one of them has an angle of theta. So in quantum mechanics, there's no way to distinguish between these two alternatives. When you cannot distinguish two alternatives in quantum mechanics, their amplitude will interfere, and then you get quantum mechanical effects based on that. So this is the origin of indistinguishability. Really, it is the uncertainty principle, and in some sense, it is also the reduction of the number of degrees of freedom. So long as you have 1 degree of freedom that's free, and you do not need to consider that in your dynamics. For instance, if you have 2 electrons, and I'm doing low energy scattering in the absence of a magnetic field, then we have 1 degree of, we have for each of the electrons, we have a degree of freedom, which is the spin that we can use to distinguish the two particles. If the energy is low enough, then as the electrons travel, the magnetic field it produces is probably too low to change the spin of the other particle. So we can use this to we can use this degree of freedom to distinguish the electrons without actually affecting the dynamical problem we're studying. So the degrees of freedom is important too. But really, indistinguishability comes from the uncertainty principle. Okay. So now, let's do a thought experiment, and let's write all this in terms of direct notation, and let's see what we can find. So suppose now we have an experiment. I have a particle incident from this side. Let's say that particle 1 is incident from here, particle 2 is incident from here. On a piece of paper, I can label it, right? Because so long as I treat particle 1 and particle 2 with the same footing, I'm still taking into account the indistinguishability. It doesn't matter if I label them 1 and 2. Okay, and then they scatter in the middle region, and then they go off. They could go off this way, or they could go off this way, we do not know. Okay. But then at position A and position B, I place 2 detectors. And the experimental result is that both detectors have a click, indicating that they have detected the particle. Right? Okay, so let's label the x coordinate, the spatial coordinate of the first particle by x1. Okay. It should be a vector. And then the other one by x2. So this is when the scattering happens at here, right? So right after the scattering, right, I have 2 possible outcomes that I cannot distinguish. One of them being particle 1 goes to, so remember these are vectors, right? But I'm not going to write their vectors. Okay. So particle 1 is at position A, particle 2 is at position B. This is one outcome that's possible, right? And then you can also have particle 1 being at position B and particle 2 being at position A. And due to their indistinguishability, our experiment cannot tell the difference between these 2 outcomes. You can think about our experiment as these two detectors. What they're really, you can model them as the 2 operators. The operators x1 hat plus x2 hat. Right? So the total operator involved in this experiment is we're measuring the sum of their coordinates. And because if they were distinguishable, this sum would be an ordered pair. Right? It will matter whether this is A is in the front or B is in the front. Right? But then now they're indistinguishable, so an ordered pair have this ambiguity here. Right? So in quantum mechanics, we know that if this is a allowed one and this is a allowed state, then any superposition of them must also be allowed. So our experiment really narrows down the state after the experiment to something like, let me use the shorthand here. So I'm saying that the eigenvalue here denotes the eigenvalue of the position of particle 1 and this particle 2. Right? So now I can only say that after the experiment, I have deduced that the 2 particle is in a state, a superposition of states given by maybe beta A B plus gamma B A. Okay. And this degeneracy introduced by, notice that if I now use this operator to operate on any of these states, I will get the eigenvalue A plus B. Right? So all these states are degenerate. And this is called the exchange degeneracy coming from indistinguishability. So now if everything is degenerate, it's hard to do quantum mechanics on this. Right? If we have so many states, you can only narrow them down to these superposition of states. But now we will do will require physically by saying that now if I do the experiment with the 2 particles exchanged, right? If I do the experiment with the 2 particles exchanged, then the physics should not change. What I mean is, if I now exchange the role of the two particles, taking this to be A, then I should not produce a new physical state, a new physically distinct state. And in quantum mechanics, what do we mean when we say two states are not physically distinct? We mean that they are related by a constant phase. Constant. Right. So I can deduce that to impose the symmetry under the exchange of particles, I can write this. Right. This is imposing a symmetry under the exchange. Alright, so now I can deduce a relation between beta, gamma, and alpha. Right, so this tells me that beta AB plus gamma BA is equal to alpha beta BA plus alpha gamma. So by matching the coefficients, I deduce that, well, alpha, beta, and gamma need to satisfy these relations. Beta is equal to alpha gamma, while gamma is equal to alpha beta. So from here we deduce that since beta and gamma are really arbitrary, we really deduce something about alpha. So alpha can only be plus or minus 1. Correct? Okay. So now what we see is that under exchange, the state can either be can either have a +1 or a -1. And now we introduce the concept of bosons or fermions. So for boson, okay, boson takes the +1 choice, and the fermion takes the -1 choice. Okay, and this is completely an empirical result. Is that every experiment we have found that bosons and fermions behave this way, and there's also some, and this thing is also related to the spin of the particle. Bosons have integer spin, while fermions have half integer spin. So if I have a half integer spin particle, it will behave as a fermion, and the wave function will acquire a minus sign under the exchange of two particles. So this is called the spin statistics theorem, and this is not part of quantum mechanics. This is an external input to quantum mechanics. So in quantum mechanics, we just take this as given and agrees with the experiment. Right. So now let's think about what are the if we just have two particles, and if they were distinguishable particles, and we have two states to choose for two particles, then what are the choices? For classical particles that are distinguishable, we could have both particles being in the same state. Right? So maybe I can write, let's use some notation. Maybe I can write omega 1, omega 1. This is an allowed state for the classical particle. Omega 2, omega 2. Well, and then I can have them exchange. Correct? And this is the classical part, distinguishable. Alright, so now for a fermion, for two fermions, we require that the wave function acquire a minus sign under the exchange of particles. So the only thing that can happen is this one. Right? And for boson, we have three choices. The wave function should remain. The same under the exchange of the particles. So we could have omega 1, omega 1. When I exchange the two particles, the wave function acquires a +1. Right? I could also have omega 2, omega 2, and then I can have a superposition of cross terms, but with a plus in the middle. Okay. So these are the possible two particle states for distinguishable particles, fermions, and bosons. And let's think about this statistically. So for distinguishable particles, I have 4 allowed states, and out of the 4, 2 of them have the 2 particles in the same state, right? So if you have 2 possible states, then it's 0.5, it's 50% likely that the particles will be found in the same state. Right? For fermions, there's a 0 chance of finding the 2 particles in the same state. Right? Okay. And then for bosons, you have a total of 3 possible states in which 2 of them you will find the 2 particles in the same state. So if you do a ranking, do a comparison, you could say that bosons are the most sociable, and then it's the distinguishable particles, and then the fermions are the least sociable. I mean, they do not like to go into the same state. In fact, they cannot go into the same state, and that is because if I have them in the same state, the wave function necessarily vanishes because they have to acquire minus 100 exchange, and that doesn't satisfy. Right? So, and this for the fermion, this is called the Pauli exclusion principle. No 2 fermions can occupy the same state. While for the boson, this has very interesting consequences because bosons like to flock to the same state. And in certain cases, if you provide the right environment, like low temperature, then the boson will favorably occupy the ground state, and you will have something called a boson-ion condensate. Right. Maybe you can investigate this in your homework or whatever. We will make use of this concept later when we talk about Cooper pairs and the Cooper pair box. So the next thing I would like to talk about is to show you explicitly that even if you have 2 non-interacting particles, the effect of having to write the wave function this way has an effective interaction, introduces an effective interaction between the particles. And this gives you an idea of why there's a Pauli exclusion principle. It's saying that there's a force actually repelling the two fermions if we carry out this calculation. So for that, let's set up the problem. Let's say that we have a 1D problem in which we have 2 particles, and let's say they can be either fermions or bosons. And the 2 particles, they are they're initially in 2 distinct states. So one of them, so this is the x-axis. This is 0. Oh, you might not be able to finish this. So let me set this up, and maybe you can do this as a homework. Okay. And so this is a. This is minus a. This is plus a. So I'll call this wave function psi minus, and this wave function psi plus. So psi minus, this wave function is occupied by the first particle, and it has x1 being it. So this is in a normalized Gaussian state. If you remember, we spent some time to normalize this Gaussian state before, and this is correctly normalized. The second particle occupies this wave function. Right. And now notice that these 2 wave packets have an overlap. Right? So we're considering, although the 2 electrons are completely free, so they're not interacting, they're overlapping. So the effect of indistinguishability is important when the 2 electrons overlap. That's what we said at the beginning of the lecture, right? So now, let's write down the correct wave function for the fermion. It must be that the correct wave function for the 2 particle state is something like, so I'm going to use the big sign. X1, X2. A normalization factor, which we cannot determine yet because the two wave functions overlap. and then multiply by subtracting their exchange term, which is correct. Okay. So now let's think about what is the energy expectation value of this two fermion state. Okay. So to do that, we're taking the expectation value of the kinetic energy operator. And the kinetic energy operator for this two free particle system is simply the sum of the kinetic energy of the individual particles. Okay. So we have H in the case of the fermions is given by P1 squared over 2m plus P2 squared. And this is simply minus H bar squared over 2m times the second derivative with respect to x1 plus the second derivative with respect to x2. Okay. So now all we have to do is take the expectation value of this thing with respect to the to this operator. Well, it's kind of complicated, but not really. Let me set up the problem for you, and you can carry out the algebra maybe as a homework. So to do this problem intelligently, let's think about what kind of. First of all these are real. All these are real. And for the normalization factor, I can always choose it to be real by ignoring the overall phase. So now then certainly after the when I do this expectation value, I'm going to be calculating something like this, n squared